Good morning. This lecture is on using integration by parts more than one time. So I hope everyone's well. So we know that the formula for integration by parts is the integral of u v dashed dx equals uv take over the integral of u dashed v dx. Okay, now remember, we choose u as the polynomial part. So x or 3x or 4x squared or 6x squared or something like that. You're going to choose v dashed to be your sin, cos or exponential part. And that's hopefully the way it's going to be. Now, if your polynomial part has the power of 1, like x or 3x, that means you only need to do integration by parts once. If your polynomial part has squared, so 4x squared or 6x squared, that means that you're going to have to do integration by parts twice. And obviously if it's cubed, you need to do integration by parts 3 times, and so on. Now there is the case where both parts are sin, cos and exponentials, but we'll come to that at a later time. Okay, so let's look at example number 1. So I just want us to integrate x squared e to the power of x dx. Remember, if you use an integral sign, you need to have dx afterwards. So u is your polynomial part, so that's x squared, and v dashed is your exponential part, which is e to the power of x. And remember, we differentiate the u, so u dashed is 2x, and we integrate the other side, and when we integrate e to the power of x, we just get e to the power of x. So we then use our formula. So the integral of uv dashed dx equals uv take with the integral of u dashed v dx. So let's fill in what we've got. So we've got the integral of x squared e to the power of x dx equals u x squared e to the power of x take away the integral of 2x e to the power of x dx. There we go. And during one application of integration by parts, that would be fine because we could then integrate that part here. But that's not the case. So now we're going to have to look at integrating this bit here. Okay, so it's separate. At the side we're going to look at now doing the integral of 2x e to the power of x dx. Now remember, keep a note of that for later, right? That's an important line of your question, right? So again, u is going to be 2x in this case, and v dashed is going to be e to the power of x. Differentiate this side again, which gives me 2. Integrate this side again, which gives me e to the power of x. So again, we know it's integration by parts because it's a product, 2x times e to the power of x. It's obviously not integration by substitution, so that's integration by parts. So we substitute that into the formula. So we've now got the integral of u v dashed dx equals uv take away the integral of u dash v dx. But this time we're using the u's and v's for this part here. The integral of 2x e to the power of x dx equals 2x e to the power of x take away the integral of 2 e to the power of x dx. And if you look, that is a function that I can integrate. So that means that the integral 2x e to the power of x dx is just 2x e to the power of x take away 2 e to the power of x plus c. Okay, but I now know what this integral here is. Right, that integral can be swapped for 2x e to the power of x take away 2e to the power of x plus c. So I'm just going to substitute that integral, or sorry, that back in place of my integral up here. So that means that the integral of x squared e to the power of x dx is x squared e to the power of x take away 2x e to the power of x take away 2 e to the power of x plus c. So that's just x squared e to the power of x take away 2x e to the power of x plus 2e to the power of x, and that's just a constant. We always just leave a constant as plus c. I know you think that the negative outside the bracket would change that to take away c, but it doesn't make a difference. Anything that multiplies c just leaves it as plus c. So that's all I would leave that as. Okay, and obviously you could, if you really wanted, you could take out a common factor of e to the power of x because it appears in everything, but I'm just going to leave that there as my final answer to that question. Right, let's look at example 2. Right, so let's choose one with a similar cost. So we want to integrate x squared cos 3x dx. That's out the way for just now. Right, so it's a product, so it's something in x multiplied by something in x. So you'd think first is the integration by parts, integration by substitution. Well, because the x squared is outside the cos or the exponential or the bottom of a fraction, that means it needs to be integration by parts. So you're going to let u be x squared and v dashed be cos 3x. So differentiate this. U dashed is 2x. Integrate this, v, and remember if you integrate cos, it becomes positive sine. 3x, and remember integrating is the opposite of differentiating. If you differentiated it, you'd multiply it by 3, so when we integrate it, we divide it by 3. So it's cos 3x over 3. So let's use our formula. So the integral of u v dash dx equals u v minus the integral of u dash v dx. So same formula, substituting the values. So integral of x squared cos 3x dx equals x squared sin 3x over 3. Take away the integral of u dashed, which is 2x times sin 3x over 3 dx. Okay, now looking at this integral here, it's quite difficult. Right, I know I'm going to have to integrate it again, but remember you can take constants out of an integral. Right, we didn't do that in the first one because it was just 2, but as soon as you put a fraction in it, it makes it a wee bit more difficult. So what I'm going to do is I'm going to rewrite this as x squared sin 3x over 3, take away 2/3 times the integral of x sin 3x dx. Okay, now again, same issue. I can't integrate that normally, so I'm going to have to use integration by parts. I'm going to look at doing that separately. So I want to integrate x sin 3x dx. 3x. Again, I'll draw a wee box around that just to remind myself where I'm going to be substituting back into later on. So, again, u is going to be your polynomial part, which is x. V dashed is going to be your sin, cos, or exponential part, which is sin 3x. So, u dashed, differentiate, gives me 1. V, integrate. Remember, sin goes to negative cos 3x, and again, divided by 3. So, the integral of uv dashed dx equals uv take away the integral of u dashed v dx. So fill the numbers in. So the integral of x sine 3x dx equals uv, so that's negative x cos 3x over 3. Take away the integral of u dash, so that's 1 times negative cos 3x over 3 dx. Right, so let's tidy that up and make it a wee bit nicer for integration. So next thing I'm going to do is I'm just going to put those two negative. Take away a negative becomes an add. And I'm going to take out, I could take out 1/3. What do you think? Nah, I'll just leave it the way it is. Okay, so I just need to integrate that now. So same thing as before, cos becomes sine. And we divide by 3, so it becomes 3 times 3 on the bottom, plus c. That becomes negative x cos 3x over 3 plus sine 3x over 9 plus c. Okay, now again, so that was integral x sine 3x dx. So what I'm going to do again is I'm just going to substitute that back into my function in place of x sine 3x dx. And remember, put the 2/3 in as well. So that means that the integral of x squared cos 3x dx is just x squared sine 3x over 3, take away 2/3, multiplied, and answer up here. So that's negative x cos 3x over 3 plus sine 3x over 9. And again, plus c. The constant doesn't change based on the 2/3 or anything like that. Constant's a constant, a number's a number. Right, so let's multiply everything out, try and make it neater. Plus 2x cos 3x over 9, take away 2 sine 3x over 27 plus c. And that is the final answer that you should get for that question. I mean, there's not even a common factor you could take out apart from maybe 1/3, but if you take out a common factor of 1/3, it doesn't make it any more neat. It just makes it even more annoying than what I've got there. Okay, right, what I would like you guys to do, here's a little worksheet that I'm going to make up. Just like I do in class. So I would like you to try and integrate x squared e to the power of negative 4x dx. I'd like you to integrate. Let's do a definite integration this time, so put your limits in at the end. We're not doing a substitution or anything like that, so we just treat the limits like normal, just put them in at the very last step. So that's x squared e to the power of x dx, and then 3 is x cubed e to the power of x dx. Now, hopefully you can spot what's going to happen with this one. It's going to take you a while, but you'll get there eventually. Okay, if you want to pause the video there and attempt those questions, I'm then going to go on to the next type of question. And this is integration by parts. And they're called cyclic calculations. Now, integration by parts is important because it can be in anything, any integration from now on, in Engineering 4, Engineering 5, or when you go to Strathclyde next year. It can be in any question could ask you to do integration by parts. It's a really, really important technique, so make sure you learn how to do it now, because it's going to be embedded within other questions, and if you're trying to learn integration by parts at the same time, then it's going to be really, really tricky. Okay, so let's look at the first one. Right, now, let's have a look at the integral of e to the power of x cos x dx. Now, this is like the type of question I was talking about at the very start. There's no polynomial part. There's only an exponential or a cos. So, as long as you keep the function the same type for the u, the exponential function, and the function the same type for the v, the cos function, or the other way around, it doesn't matter. As long as you keep doing the same thing for u and v, it will eventually work out. So I'm just going to let u be the exponential part. Arma? Yeah, let's just let u be the exponential part, and let v dashed be the cos x part. So let's differentiate that. So u dashed equals e to the power of x. So that means that v is just sine x. So let's use our formula, same as before. So the integral of u v dashed dx equals uv, take away the integral of u dashed v dx. So we've got the integral of e to the power of x cos x dx equals e to the power of x sin x, take away the integral of e to the power of x sin x dx. Now, this is the bit that we're hoping we can integrate. But I've got the exact same problems I had in the initial question. I've got a function with x multiplying another function with x. So let's try integration by parts one more time. That's why it's a cyclic calculation. I'll show you what I mean by that. So I'm now going to integrate e to the power of x sin x dx using integration by parts. So let u, and as I said, let u continue with the same format. So u is going to be the exponential, because otherwise you're just undoing what you did in the first step. and v dashed is going to be sine x. So that means that v is just negative cos x. So the integral of u v dashed dx equals uv minus the integral of u dashed v dx. Let's substitute in our two values. The integral of e to the power of x sine x dx is negative e to the power of x cos x, take away e to the power of x times negative cos x dx. Okay, so that just becomes negative e to the power of x cos x. So that's just going to give you negative e to the power of x cos x dx. But again, just like I would always do, so hold on, that's not a t, that's a bracket, just so you can see. I'll just give you some time. So substitute in your values of u and v, u dash and v, and then e to the power of x times negative cos x is giving me that thing there. Now I'm just going to simplify, just like I did before, the two negatives next to each other and make that add. But I'm now back at square one. That's the integral I started with. So how am I going to get rid of the integration sign and the dx? So what I'm going to do is I'm going to substitute what I've worked e to the power of x sine x dx back into my first integral, just like I would do in a normal integration by parts question if I had to do it twice. So got the integral of e to the power of x cos x dx equals e to the power of x sine x, take away negative e to the power of x cos x plus the integral of e to the power of x cos x dx. So that gives me e to the power of x cos x dx equals e to the power of x sine x, take away e to the power of x cos x, take away the integral of e to the power of x cos x dx. Right, so I've still got an integral sign, but if you look at my original integral, that is the same as the other integral that I have in my equation. So just like I would do with any equation, if I take that over there, that would mean I'd have two of them, because if you put one of them here, take away one of them here, so if you move that over it becomes an add. So that means if I move that over I would have two and that would equal e to the power of x sine x, take away e to the power of x cos x. Now, because I've used that trick, I've actually integrated it. So I just need to take that over and divide it by 2. And obviously, because it's an integration question, even though I've used a trick to get there, this cyclic method, because it's the only way I could do it, I put in plus c. And that would be the way you would do it if you had a non-polynomial part. You just had sin, you just had exponentials, you just had something like that. So an example for that, and just a question for you to try at home. I'll just put that on the bottom of that other worksheet that I gave you. So let me just grab that. There we go. So that was your worksheet for the two applications of integration by parts. So this is 4, and this is a cyclic calculation. So I'm going to start it off for you. If I wanted to work out the integral sine x over e to the power of x dx, that's not what I would do. I would work out the integral of e to the power minus x sine x dx. So that's what I want you to do. So those are the 4 questions I would like you to try. And I will upload the answers onto Moodle on Friday. Good luck. Any questions, please message me on Teams. Hope everyone's well. Hope everyone's having fun being stuck at home.